All right, today we're taking a deep dive into one of the most mind-bending topics out there, the physics of orbiting a black hole. I mean, it's this ultimate cosmic dance, right? And it's governed by rules that completely warp our sense of reality.
Which, of course, brings up the most obvious question. Can you even orbit a black hole? I mean, seriously, it's a thing that sucks in light. How could you possibly circle around it? Well, the answer? It's not as simple as you might think.
So, the short answer? Yes, absolutely. You can orbit a black hole. But, and this is a massive but, it is all about location, location, location. You see, there's this critical line in the sand. Stay on one side of it, and you can waltz around that black hole for eternity. But the second you cross that line, well, the dance is over.
Okay, so to really get our heads around just how wild this gets, we need to start with the basics. Let's rewind the clock a bit and go back to the familiar world of Sir Isaac Newton, where gravity is, well, it's nice and predictable, tidy even. You see, in Newton's universe, gravity follows this really clean and simple rule, the inverse square law. All that means is that every single orbit is a perfect, predictable shape. They're what we call conic sections. And it's just like it sounds. If you were to slice through a cone, you'd only ever get one of four possible shapes. And what are those four shapes? Well, you've got your circles and ellipses. Those are your bound orbits, where you're basically stuck on a gravitational leash forever. Then you have parabolas and hyperbolas. Think of those as cosmic flybys, just one-way trips. And in Newton's world, that's it. That is the entire menu, just four options, period. But here's the most important part of Newton's rules. There's a kind of built-in safety feature. As long as an object has even a little bit of sideways motion, this sort of invisible energy wall pops up near the center that just prevents it from ever falling in. It's like a cosmic guardrail. You're always safe.
Okay, but that's the nice, safe Newtonian universe. Now, let's get closer to the black hole. We're about to leave that comfortable world in the rearview mirror and step into Albert Einstein's territory. And trust me, this is where gravity gets really weird.
And here's the culprit right here. Einstein's theory adds this little correction to Newton's clean equation. See that extra bit, that inverse cubed term? Now, most of the time, it's so ridiculously small you wouldn't even notice it. But when you get into the crushing gravity near a black hole, that one tiny term changes the entire game. So let's look at what that one little change actually does. Under Newton, you get perfect, stable shapes. But with Einstein, the orbits start to wobble. They can become unstable. They can even form these crazy patterns we'll talk about called zoom whirls. And here's the biggest difference of all. Since nothing can go faster than light, there's suddenly a minimum distance, a point where you simply can't orbit any closer.
Okay, so the very first clue that things are different is something called orbital precession. A normal Newtonian ellipse is simple. It's a closed loop, tracing the exact same path over and over. But a relativistic one, it doesn't quite close on itself. Every time it goes around, the whole orbit shifts just a little bit, creating this amazing rosette pattern, kind of like a spirograph. And this isn't just some abstract idea. We actually see this happening with Mercury's orbit. It was one of the first big proofs that Einstein was right.
All right, so let's push even closer. We are now entering what's called the whirl zone. This is the real danger zone. We're so close now that gravity is just off the charts, and it starts to create some of the most bizarre and unstable orbits you can possibly imagine. And our first stop is a critical boundary called the ISO. That stands for the innermost stable circular orbit. And you should really think of it like trying to balance on a knife's edge. This is the absolute closest you can get and still have a stable circular orbit. If you're here, even the tiniest push, I mean the slightest tap from a thruster, is going to send you either flying off into space or, much more likely, spiraling down into the abyss.
So how close are we talking? Well, for a standard non-rotating black hole, the ISO is at a distance of 3 Rs. Now, Rs is just the Schwarzschild radius, which is really just a fancy way of saying the size of the black hole's event horizon. So the last stable circular orbit is at 3 times the radius of the black hole itself. That's a real physical line drawn in space-time.
But believe it or not, we can actually get even closer. There's another line, the IBCO, or the innermost bound circular orbit. This is the absolute final frontier. An orbit here is technically possible, but it is wildly unstable. In fact, to even try to orbit here, you would have to be moving at the speed of light. And that's why it has a much cooler name, the photon sphere, because only photons, particles of light, can even attempt to walk this tightrope.
So what on earth happens in that chaotic space between the stable orbit and the light speed orbit?
You get these absolutely wild patterns called zoom-well orbits. The name says it all, really. An object will zoom way out into a big loop, then dive back in and whirl around the black hole a few times super close before zooming out again. It's this beautiful, almost frantic dance that an object does right before it takes its final plunge.
Okay, so we've seen all the boundaries and the crazy dances. But what happens when you finally cross that last line? And what if the black hole isn't just sitting still? What if it's spinning? Let's talk about the final plunge and the ultimate twist in the story.
So why is it inevitable? Here's the best way to think about it. In Newtonian physics, there's this potential energy hill that gets infinitely steep the closer you get to the center. It's basically a wall you can never get over. But with relativity, that hill has a peak, and that peak is right at the photon sphere. And once you roll over the top of that peak, there's no more hill to climb. The path only goes down. There's no wall, no safety net. The only way is in.
Now, up until this point, we've been talking about a simple, non-spinning black hole. But here's the thing, most of them aren't stationary. They spin, and they spin fast. And a spinning black hole doesn't just curve space-time, it grabs it and twists it. This effect has an awesome name, frame dragging. The perfect way to picture it is to imagine a spinning bowling ball in a giant vat of honey. It doesn't just sit there, it drags the honey around with it. A spinning black hole does that to space itself.
And this cosmic whirlpool has a huge effect on any orbit. If you're moving in the same direction as the spin, that's a prograde orbit. Then this frame dragging actually gives you a little boost. It pulls you along for the ride. But if you try to orbit in the opposite direction, a retrograde orbit, it's like trying to paddle a canoe upstream against a raging river. The very fabric of space-time is pushing against you, fighting you every step of the way.
And just look at the difference this makes. It's absolutely staggering. For a black hole spinning as fast as possible, if you go with the spin, your stable orbit can get all the way down to the event horizon itself. You can practically skim the surface. But if you try to go against the spin, the last stable orbit gets pushed way, way out to 9 times that distance. 9! So going with the flow lets you get incredibly close, while fighting the current keeps you incredibly far away. It completely changes the rules of the game.
But we've saved the most mind-blowing part for last. What if your orbit isn't perfectly lined up with the black hole's equator? Well, that space-time tornado we talked about, it literally grabs your entire orbital plane and starts to twist it. All of a sudden, your nice, flat, two-dimensional orbit is gone. Instead, you're forced onto a wild, spiraling, three-dimensional path through warped space-time.
And that just leaves us with this final, crazy thought. Think about where we started, with Newton's nice, tidy, flat orbits, like a record spinning on a turntable. And where do we end up? With Einstein's three-dimensional space-time twisting dance. So if something as basic as a flat orbital plane can get twisted and warped into 3D, it just makes you wonder, right? What other fundamental rules of reality are being completely broken and rewritten right at the edge of a spinning black hole?